Hello everyone, welcoming you all to the problem solving session on topology. Today we will discuss a problem in Munkres from exercise 2.7 P8 that is related to metric topology.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
So here they are saying that let X be a topological space and Y be a metric space. So some metric is defined on that and that metric topology is put on to Y. Fn be a sequence of continuous function. Sequence mean Fn is defined for all n in natural numbers. And it is also given that the sequence xn of points of x converges to x. Let's quickly see what does it mean to converge. It is simple. Suppose in the space x, capital X, you take the point x and consider any open set around x, say u. Then there exists capital N in natural numbers such that xm belong to u for all m greater than or equal to the capital N value. So basically xn, xn plus 1, everything will be there inside that u. This must be true for any open set u around x. That's what we mean by convergence. So this sequence converges to x. Then we have a condition on uniform convergence. First, let's see what is uniform convergence. They are saying that the sequence Fn converges uniformly to f. Fn, the sequence of functions Fn, converges uniformly to x. This is a uniform convergence. So that means that it is simple. For any given epsilon greater than 0, there exist capital N in natural numbers such that f n of x belongs to the open ball around f of x with a radius of epsilon for all n greater than or equal to n, and all x in x, in capital X. So simply they mean that if you take the space y, there will be the point f of x, right? For any x. This is true for any x, or you can take some s, suppose f of s. Then there exists a capital N value such that if you take this epsilon ball around this space capital Y, then let's say the capital N is capital N and f capital N of s and f capital N plus 1 of s all will be inside this epsilon ball. And this is true for all s in the set X. That's what we mean by uniform convergence. Because for all points in capital X, the f function is converging uniformly, right? Because the capital N value is same for all open balls around that f of s. So with this definition, let's look at the question now. We want to prove that if the sequence fn converges uniformly to f, then prove that fn of xn converges to f of x. So this might be little tricky when seen directly. So let's first look at a theorem. What is the theorem? It is a simple theorem to start with. It states that let Tn be a sequence that converges to T, then if f is a continuous function, f is continuous function, f of Tn converges to f of T. This is the theorem. The proof is very simple. Suppose, let us take the space from A to B, the function, that function let us call it to be f, and assume that it is continuous. Now, if you take f of t, consider any open set around f of t. Let us say u. Now, consider f inverse u. Now, obviously, that should have t, right? By definition of functional inverse. Now, we know that any open set around t will have a value capital N such that t capital N plus 1, t capital N plus 2, and so on. All of them belong to this set, right? And that would imply us that f of Tn and f of Tn plus 1 and so on are all inside you. So I can say that f of Tm belongs to you for all m greater than or equal to n. And that's why I can say that f of Tm or f of Tn converges to f of t. So using this result, let us try to solve the question. We are interested in fn of xn, remember. So let's go step by step. First is the step 1. There are only 2 steps to understand. First is the step 1. What is our aim? Let us first write our aim. Then we will jump into step 1. Aim is that in any open interval around f of x, or I can take any basis element around f of x. We know that metric topology is put on the space y. So the basis elements are epsilon balls, the epsilon open balls. So that open ball should have some value, say capital N, such that I have to prove that there exist capital N in natural numbers such that fm of xm, let's call this open ball to be u, fm of xm belong to u for all m greater than or equal to n. That's my aim. With this as my aim, let's go to step 1. I will consider f of x. Instead of taking now epsilon ball, I will take an epsilon by 2 open ball, a smaller size open ball. Let's make it a little larger so that it's easy for analysis. Let's tell that this radius is epsilon by 2. Since xn converges to x, and we know that f is a uniform, fn converges uniformly to F. So F will also be continuous. So we have one more conclusion here, that since Fn converges uniformly to F and Fn are continuous function, then that implies that F is also continuous. You can prove this easily. Think about that. But let's assume that F is continuous. So obviously, then f of xn converges to f of x, right? And let us say that for this epsilon by 2 open ball, the value of capital N be some n1. For example, let us take 200. So f of x 200 and then f of x 201, f of x 202, f of x 203, all of them will be inside this. It will just go on. All of them will be inside this open ball. That's the definition of this capital N, right? Okay. Now, coming to the uniform convergence of Fn, where can I use that? That is my step 2. Assume that, since let's go back to the definition of uniform convergence. Given epsilon greater than 0, there exists a n, right? That for any x, the ball, the open ball will contain all Fn values greater than n. So let me now consider, given epsilon by 2, which is obviously greater than 0, again there exists n, right? Let us say that value to be n2, and for example I will take suppose 414, suppose I will take. But anyways, let's also keep the general proof as it is. Let's say that is n2, such that Fn of x belong to the open ball in the metric around f of x, comma epsilon by 2 for all n greater than or equal to n2 and for all x in x. So by that logic, let us copy paste this. Yes, for that, by that logic, we will see something interesting. There should be this point f of x 414, right? And f of x 415 and f of x 416 and everything and so on. Let us take value capital M to be the max of n1 comma n2. So here it is the maximum of 200 comma 414, right? Which is 414. Now you could see that now around 414 build epsilon by 2 open ball. Let's do that. Around 414 build a epsilon by 2 open ball like this. Now obviously, by the definition of uniform convergence, the n2 value must be inside this ball, right? Must be inside f of x. Here x is what? X is equal to, let us take this to be s, so that we are not confused with the terms. So s and f of s for all s in x. Let us consider that s to be x 414 now. So around 414, if you construct the epsilon by 2 ball, so this is an epsilon by 2 ball, then that should have the point f 414 of x 414, right? Because for all n greater than or equal to n2, it must be present in the open ball. And also f415 of x414, f416 of x414, everything will be there. But that's not our concern, it will just confuse us. So f414 will be inside this ball. And also remember that the distance of f of x comma f of x414 is less than epsilon by 2, and the distance of f of x414 comma f414 comma x414 is less than epsilon by 2, because it is also present inside this green ball. So summing up, we get that distance of f of x by the triangle inequality, f of x and f414 of x414 is less than epsilon by 2 plus epsilon by 2, which is equal to epsilon, right? So in the entire epsilon ball, this 414 point f414 of x414 is present. And now I claim that fn of xn belong to this open ball, belong to the open ball of x with epsilon for all n greater than or equal to capital M. Because if you take f415, sorry, x415, you can find f of x415 here. Now similarly construct a epsilon by 2 open ball. Similarly construct a epsilon by 2 open ball around f x415. Now this must contain the point f414 of x415 and f415 of x415 by the uniform convergence, because we know for all n greater than or equal to n2 it must be in the open ball. And similarly for 416, 414 will be there, f415 will be there, f416 will be there. So everything is present, and hence my aim is done. I have proved my aim, and that proves the question, right? Now this lets us to think, is the converse of the statement true? That is, if fn of xn converges to f of x, or fn of x converges to f of x, is it true that fn converges uniformly to f? Is that true? There is a good example in Munkres of this in problem P9. I'll just state that example briefly. So that example is that considering the function fn of x in the fn of x is 1 by n cube into x minus 1 by n the whole square plus 1. And let's consider f of x to be the 0 function. Obviously f of x is continuous. First let's prove that fn of x converges to f of x. Also you can think about proving that fn of x is continuous. That will be easier. But here remember that fn and f both are functions from R to R. This function looks like the following. So here I have plotted the fn function This plot is also available in the Munkres. So here it is showing the fn of x as the y value and x as the x value. We will prove that fn of x converges to f of x. It is true because if you take any value of x, let's say x naught, let x be equal to x naught, and you take a open interval around f of x naught. So suppose x naught is here, and we take an open interval, epsilon open interval around f of x naught. We know f of x naught value is 0, so I just consider the interval minus epsilon to epsilon. And since we have to prove the convergence, I have to find the capital N value such that all fn of x naught belong to this open interval. Now, what is fn of x naught? It is 1 by n cube into x naught minus 1 by n the whole square plus 1, right? And that has to be, this is obviously positive, so it is greater than minus epsilon. But I have to find n such that it is less than epsilon. And I have to prove that the capital N value exists. That is easy. Because if you take 1 by epsilon and epsilon is greater than 0, so I can do this 1 by epsilon and it is positive also. Minus 1 must be greater than n cube into x naught minus 1 by n the whole square. Now notice that for sufficiently large n value, sufficiently large n value, the entire thing can reach a very large value, right? That is more than 1 by epsilon minus 1. Right? The reason is because for sufficiently large, this is almost equal to x naught square for sufficiently large n. And you just keep on increasing n such that more than that such that 1 by x naught square into 1 by epsilon minus 1 is less than n cube. Since x naught and epsilon are fixed, given to you, I can find n value such that it is greater than this. Let us say that value is n cube. Now I can say that fn of x naught belongs to minus epsilon to epsilon, or the open ball around f of x naught for all n greater than or equal to capital N. Right? Okay. Now we know that fn of x converges to f of x. But we will now prove that fn of x do not converge uniformly to f of x. That will be easier to see because we can see that the 1 by n will always take a value 1, will always assume a value 1. However large or small n you take, however large n you take, let's say 10 power 20, this 1 by 10 power 20 will now take a value of 1, right? And suppose if that epsilon value is 1 by 2, we cannot find a capital N such that fn of x is in the interval minus 1 by 2 to plus 1 by 2 for all n greater than or equal to some capital M. This is fine. This is just the convergence of fn. But this is not fixed x because this is now uniform. We are talking now about uniform convergence. So we want to additionally prove that for all x in the real numbers, basically the domain, which is the real numbers. But obviously, it is not true. As if you take x is equal to 1 by 10 power 20, this will not be true for that particular fn. Now, again, if you increase n, you can come up with a contradiction for this uniform convergence by taking x is equal to 1 by n. So, it is not uniformly convergence, and hence the converse is not true. I will stop here. You can keep thinking about this more and try to come up with a proof for if fn converges uniformly to f and fn is a continuous function, then try to prove that f is continuous. So, thank you all.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.